Now we will see what happens with the fundamental theorem of curl, the third type of derivative related to a vector function. It says that the integral of curl of a function over a surface S. So since it involves a surface integral, we dot this vector function with the surface normal dA bar multiplied by the surface element is equal to the line integral over a closed path P of V bar. So it is saying as if we consider a surface S and there is a vector function V bar in space. Now the curl of this vector function V bar over this given surface S integrated over the entire surface is equal to the value of line integral of the same function V bar along the path which encloses the surface S. Now we should note that this surface need not be unique. That is, if we take a path which is of circular nature, the surface could have been a spherical dome upwards, the surface could have been a spherical dome downwards, or the surface could have also been a flat disk. In all these three cases, though the surfaces are different, but since the boundary is the same and the right hand side only involves a closed integral over a given path or a given boundary, the values of the left hand side for all these cases will be the same. So this integral does not depend upon the surface chosen. Does not depend upon the surface chosen. That's the reason why if this integral is over a closed surface, that is del cross V bar dot dA bar over a closed surface, this is going to be 0. So these are two corollaries of this theorem. Now let us just try to verify the theorem for a given example. Suppose V bar is a slightly complicated function of this type 2xz plus 3y squared y cap plus 4y z square z cap. Yes. And now we have to verify the above theorem for this V bar for a surface lying in xy plane which is a square. So just change the plane. So the plane chosen in the example is different. So if this is the x-axis, this should be the y and z1. So the plane lies in the yz plane. The surface lies in the yz plane. So the normal vector dA bar points in the x cap direction. So x cap into the small displacements are namely dy and dz. So dA bar in this case is x cap into dy dz. So we have decided the dA bar. Now we can, for this particular V bar, we can find out del cross V by following the definition of cross product. So I cap, j cap, k cap, dou by dou x, dou by dou y, dou by dou z. Then the x, y and z components of V bar, that is 0, since this does not involve any x component. Then dy component is 2xz plus 3y squared, and dz component is 4y z squared. Now this can be solved and we see that this is equal to just 4z squared minus 2x x cap plus 2z times z cap. Now this we have to integrate. Before that, this del cross v bar has to be dotted with dA bar. That is to be dotted with dy dz x cap. So we can see that this z component is going to disappear. So we are left with 4z square minus 2x into dy dz. Now this has to be integrated over the given surface. We can solve this readily. We can see that this is just equal to 4 divided by 3, as we see the limits from on y are 0 to 1 and limits on z are also 0 to 1. This is equal to 4 by 3. So this is the left hand side of the equation. Now the right hand side is slightly complicated as it involves some path. Though it is a closed path, let us choose a direction which is of anti-clockwise manner. We usually choose this direction by right hand rule. So since dA bar was pointing in the x cap direction, the obvious rotation would be, if this arrow represents the thumb, then this rotation represents the curl of fingers. That is the right hand rule. So we choose an anti-clockwise direction for a dA bar pointing in x cap direction. So there are 4 subpaths involved: path I, path II, path III, and path IV. That is 4. So we can solve the line integral for each of these paths. That is v bar dot dl bar for path 1, path 2, path 3, and path 4, and then we can add up these 4 line integral values. So the values in this particular case are namely 1, 4 by 3, minus 1, and just 0. So we add up these 4 values, these just cancel out, and what remains is 4 by 3. So yes, the right hand side is also 4 by 3. So in this particular case, this theorem of the fundamental theorem of curl appears to work. We can verify this theorem for n number of such functions, vector functions v bar, and we can always see that this theorem works for all such functions.